Let's take a look at a bipolar junction transistor, and we're going to look at the K value, and that's the beta sensitivity, okay? So the DC operating point in some biasing configurations is dependent on the value of beta. In other configurations, it has almost no dependence. So it's desirable to have a biasing circuit in which the value of beta doesn't matter, okay? So in this circuit here, this is a common emitter circuit, and we have the base resistor is 1 meg, and then our collector transistor is 5K here. And this one here happens to have a K value of 1, and so we take our 20 volts here into our 1 meg ohm resistor here. That means we have 20 microamps on the base, and since we have a value of 1, we multiply that by our beta. In this case it happens to be 100, so we have 20 microamps times 100. That means that the collector current is going to be 20 milliamps, okay? So here we are over here. Our base current is going to be 0.02 milliamps here. And then if we put an AC signal on here, say that the peak is going to be at 0.001 milliamps, okay? And then coming out of the collector current here, we got our times our beta here. It's going to be 100, so it's going to be 2 milliamps of DC here. And then our AC value is going to be, we'll just say it's 0.09 milliamps, okay? So that means that our DC beta is going to be equal to 100, our 0.02 milliamps into our 20 milliamps, and then our AC beta is going to be equal to 90. Now, the DC and AC beta are usually close in value, and a lot of times we just go with the DC value. So here we're just going to be concerned about this the DC value here. So now the beta, it's an unstable quantity. It changes with temperature and the DC operating point of the transistor, from one transistor to another, okay? So what's this DC operating point? So here's our graph here, and this is the collector current, and this is the voltage here on the collector. So now this top value, this 4 milliamps, well, how do we get that? Well, we have 20 volts and we have a 5K resistor, so that means the most that can come through here is going to be 4 milliamps. So that's going to be our saturation there. That's as high as we can go. And down here at the bottom is going to be our 20 volts. We can't get any higher than that, okay? So where's our DC operating point? Well, we have 2 milliamps here on the collector current, right? And this 10 volts, where do we get that from? Well, we've got our 2 milliamps going through our 5K resistor, and that's going to be 10 volts, and so we take our 20 minus a 10, so our DC operating point is going to be at 10 volts down here, okay? Now that's going to be a perfect spot to have it, because we can have our AC signal now riding up and down on here, and it's going to be fine. But say we change the beta of this to 200, put a different transistor in there, and it's going to be 200. Well, that means that our DC operating point is going to be way up here at the saturation point, and that's going to clip off the top of our AC signal, okay? And the same thing with this. If we change this value here and we bring this DC operating point way down here, then we're going to be clipping the bottom of the signal off down here. So we want to keep the DC operating point right in the middle between the saturation point and our cutoff point there. So now there are better ways to bias a transistor so that the percent change in collector current is less than the percent change in base current, okay? So this K, it's a constant of proportionality, okay? So if K of 1 means that your base current and collector current are going to be just dependent on the beta. So base current times beta is going to equal to your collector current, okay, with a K value of 1, okay? Now, you can get the K down to, say, 0.01, or a lot of times it'll be at maybe 0.2 or 0.1. Now, so in this case here, we have an emitter bias here, and so our K value in this one is going to be equal to 1, but we divide that by 1 plus the beta. We take our beta, say I have 100, times our emitter resistor here, and then we divide that by these two in parallel here. So you can see that by changing these resistors around, we can get our K value down to, say, you know, 0.02 or something like that. So if we change the beta here from, goes from, say, 100 to 200, it's not going to matter in our circuit. Our DC operating point is going to stay in the center here, wherever we have it. And our AC current voltage can ride up and down on that. So that's what you want to do. You want to design a circuit with the lowest K value you can, the beta sensitivity. So that's our K value, just the beta sensitivity. How sensitive is the circuit to this beta value? Okay, so that's that's all it is. The lower the K value, the better. So thank you.